Right, so this is going to be just a little talk on designing a PCB in KiCad. It's not going to be anything particularly special. There are certainly much better, sort of how-to guides, much more in-depth that you can find out like on YouTube and that sort of thing. So don't expect, too much from this really. It's just going to be, here's a simple little circuit, how to put it into a schematic and then put it onto a PCB, generate some Gerbers and then order them from someone like JLC PCB. Yeah, so this is basically completely off the cuff. I haven't prepared any slides, I haven't rehearsed anything. So yeah, basically I kind of want to make it maybe just like completely free form. Like if you've got any questions at any time, just like jump in and ask. Yeah, and then whatever's left, I guess we'll just cover at the end of it. Let's see, share my screen. Host is disabled, participant screen sharing. You have to let me share my screen, Dave.
Try now.
There we go. All right, now which one is it? It's going to be this one. Oh, allow Zoom to share the screen or consistent. This is not going to go well. One moment. Probably gonna have to. Yeah, it's gonna need me to restart. Oh dear. Okay. I'm gonna have to probably jump out and then jump back in again to allow Zoom to record my screen. So give me a moment. Okay, let's try this again. Yeah, screen. Yeah, there we go. All right, now, can everybody see that?
Yep, I can see it fine.
So what I've got here is a very simple little simulation. It's a very simple game, you might say. I think it's called like Kill the Bit or something, and it's basically just a series of flip-flops. The idea is that you sort of inject a bit, and then like maybe a two-player game. So like one person say injects a bit or maybe multiple bits into like just sort of like a circular sort of shift register, and then the other player has to kind of kill those bits off, so they have to sort of clear them out. And the basic way that this works is that you have a clock down here, and that is basically just clocking a bunch of shift registers which are all connected like straight together, and we have one little XOR gate in the middle with a button hooked up to it, and that's kind of what will allow us to sort of inject and clear or set and clear a bit within the shift register. So as an example, if I just push the button, we're going to see one bit sort of come in, and then it'll just keep making its way around this series of shift or flip-flops. And the idea would be that sort of when the bit sort of comes up, you kind of got to click the button to sort of clear it out and get rid of it. So yeah, and it's kind of like if you just sort of hold the button, you can inject multiple bits. You can sort of inject some a random pattern, but you can't like exactly just sort of hold the button down to try and clear bits out, because you're going to end up you're basically just going to invert whatever bits are in there. So you kind of have to, be on the ball with clicking the button at the right time. Now this is quite a slow clock, which makes it very easy to do, but I think this is about as fast as I can make the simulation go. It's like 2 hertz or something like that. But in the circuit, what I'll do is I'll just design in like a little 555 timer circuit to sort of act as a clock, and then you can adjust the speed on it and make it as difficult as you want. So that's kind of what I'm going to design. I've just done it with 6 flip-flops here, but in the next version I'll kind of extend that a little bit. And just to make it maybe a little bit more difficult, I've kind of sort of left a couple of these little indicators off the end so that the bits will kind of disappear for a little bit, and then they'll lead in on the left-hand side with like 1 or 2 sort of LEDs worth of sort of preparation, just to sort of mix it up and make it a little bit more challenging. So getting on with the actual PCB side of things, this is kind of like actually, can you still see that, or am I stuck on another screen?
Still good.
Still good? Okay, cool. So this is the KiCad sort of default window, load screen or whatever. And from here, you can kind of launch into a whole bunch of different sort of tools that it has. So you've got your schematic editor, symbol editors, and footprint editors if you want to create your own components if they're not included within the sort of default libraries, PCB editor and stuff like that. And at the moment, I don't actually have a project, so we want to sort of start by going up to the file menu and just sort of going new project, creating a project to work from. So I'll just create a new one back here somewhere. We'll just call it Kill the Bit, and we'll create it there. So this is sort of a project now. I think, is that actually, we might have to say, guys, and give it its proper name, or if I just called it untitled, save as all right, there we go. So we've got our project now called Kill the Bit, and you can sort of see over here that it's sort of already created 2 files for us, the schematic and the PCB. And the first thing that we want to tackle is the schematic itself. So we just double click on the schematic file, which is .sch, and that will bring up the schematic editor. And it's basically just a page. It's got sort of like a little frame around it, so you can kind of constrain the size of your design, but you can change the size of it if you like. To change the size of it, if you did want to, basically there's a lot of hotkeys and stuff that you can use in KiCad, which is kind of nice actually. It's one of the things that because I came from Eagle, and Eagle was kind of more command based, or you just sort of do everything with the mouse if you don't want to sit there typing commands. I never really got into typing a lot of commands in Eagle. It was just basically all sort of mouse work. But the one key that I use the most in KiCad is the E key, which is basically for edit. So you basically just want to hover your sort of mouse cursor over something and then click the E key, and that will sort of bring up an edit window. It's not strictly where the crosshair is, it's sort of more where the tip of your mouse cursor is, and I can sort of maybe demonstrate that. But if we just sort of hover somewhere over this little bit down here in the bottom right hand corner and hit the E key, that sort of brings up the settings for the page in the schematic editor. And from there we can adjust the size of the page. So I don't know if it probably will fit on an A4 page, but if I want some more space, I can change this to A3, hit OK, and then that gives me a whole lot more space to work with. So that's kind of like a basic sort of thing that you'll probably find yourself using a lot is wearing out your E key basically. Right, so with well, actually, maybe I'll cover this as well. Within this edit sort of window here, you can actually set like some different information within this little box down in the bottom right. So that you can set a little title. You can put some other bits and pieces in there if you like. You can also put the date that it was sort of generated and that sort of thing. Revision 1. We click OK, and then that kind of fills in some of these fields down here. So if you're working on like a big schematic, multiple pages, you can sort of, I think you can fill in a bit more information maybe up here. Let's just put ABC in there or something. Yeah, so you can put some extra information in this box here, like maybe some notes about, what that schematic is or what that particular page is, or I don't know how this stuff sort of goes. It's probably a standard sort of format about all the stuff that goes in here. But yeah, very basic sort of overview of setting up your schematic page. From there, your next job really, I guess, is just to start adding components. So to do that, you see all these menus like around the side and on the top here. You've got things like your whatever unit you want to work in, so inch millimeters or mils and millimeters. But probably the next one we want to use really is this one over here. It kind of looks like an op amp symbol. But this here basically will allow us to start adding in components. We can use this to load up the basically all of the symbols and stuff that are available by default within KiCad's libraries. And the thing that I want to start with is a 555 timer. So I'm just going to search basically for 555, and then we just want to find a 555, sort of symbol here. You'll probably notice that there's a few, with the same sort of basic part number. And I think that the whole point or the whole deal with that is that some of them will have a default package associated with them. So for example, any 555D seems to be like a surface mount package, whereas any 555P is more of a dip package. And I'll probably focus on dip packages in this particular schematic, or this circuit. So I'll just choose this one here, the 555P. We'll chuck it in and just place it somewhere for now. Different to how Eagle works. Like in Eagle, you could sort of place multiples of the same thing just by continuing to click. But if I click again, KiCad will kind of bring me back into the, sort of select a symbol window here. So if you wanted to do multiples, you would basically just end up probably canceling out the sort of add symbol function and just sort of, like start copy pasting. But I guess the next thing we need for a 555 will be a couple of resistors and capacitors. So very simple for resistors, you just search for R, and that just sort of gives you like I think maybe more like there's different like sort of styles of resistor symbol. I don't know, some of them have the little zigzaggy line. I don't know where that is. It might be like a regional setting or something, but this sort of seems to be, I guess, the default one that comes up for me. But yeah, you might find some settings somewhere to change that to sort of suit your style a bit more. So we'll just start with by placing a resistor in. Then I'm going to find the symbol for a capacitor. And then I also want to find the symbol for a variable resistor. So R variable, because we want to be able to adjust the time or the duty cycle of the frequency, sorry, of the 555. So I'm going to grab one of them as well. And I think that's probably about it to sort of make a start. Along with the E key, the escape key is quite useful. So when you've got this sort of add symbol thing sort of selected, you can use escape to kind of cancel that out, cancel it, and just go back to like a plain mouse cursor, which you can then use to start copying and pasting some things. So I think for this, I'm just working off a little picture I've got off to the side here, but I think I want another resistor, and probably, if we're going to do it well, maybe a bypass capacitor for the 555 as well. Clicking on the symbol, we'll just sort of select it, and you can kind of highlight it, move it around. To make a copy of this, it's just literally Control-C, Control-V. So you can add a another component with just like regular copy paste. Oh, actually, one other thing we are going to need is some supply, power supply sort of symbol as well. I think plus 5 volts will give us our little power supply. And we've also want ground as well. Okay, so we've got a bunch of components and now we need to hook them all up. So the tool to do this is basically this sort of this is the 4th symbol down, add a wire, which you can also use the W key to access. And the wire is kind of how you start drawing your nets and linking things together. So scroll wheel that sort of zooms in and out. So it's nice and easy to navigate. So what have we got? I'm going to copy this off here. So it looks like pin 8 is our power supply. I'll just grab a capacitor symbol here. I'll just chuck it over here. We've also going to ground. Something else to mention as well. The default grid in KiCad, if you right click on the schematic sheet, you can sort of get to a menu with a grid. The default grid seems to be 50 mils, and I kind of like working in 100 mils because it sort of spaces things out quite nicely. It sort of makes me feel a bit more like I'm working in Eagle. But you'll sort of notice that, for example, with the 100 mil grid, I can't quite get to that pin, this end of the capacitor pin here. But what I can do is if I sort of hover over this ground symbol, and if I click, then I start drawing like a wire. And I think it's what's it going to be on the computer? Maybe might be like maybe the Windows key or Control key or something will kind of get you into a bit of a mode where you can kind of, it'll sort of snap kind of halfway through the grid. So that will kind of let you join up these two pieces here. But the other way to get around that would be to right click and go to the grid and change it to 50 mils. And then you can sort of draw the wire in between. I find that a little bit sort of repetitive and a bit annoying because you've got to kind of keep changing between the grid, and then maybe sometimes you forget to change it back. So I sort of found that the maybe the easiest way is just I don't know how I even found this key, but like just hitting like on my Mac, it's like the what is it? Will be the command key, I think. That sort of gets me into this mode where I can sort of draw a half sort of grid line and get those two connected. This is going to be a little bit more interesting here because I'm not going to be able to click on that to actually start drawing. But if I go to W or like click on W and get it over here, I can start drawing the wire. I can draw it out to here, line it up with that, hit my command key again, and then connect it up. So that's just like a little thing that I found before I would mention. If you sort of find yourself like trying to get something to join up and you can't quite do it, yeah, just have a play with some of those sort of functions. So that's kind of our power supply to the 555. We'll join up the ground. And then the next bit is going to be interesting because it doesn't really match my drawing here that I'm working from. But we need a capacitor or a resistor from VCC 7. I can give myself a little bit more room. So clicking and dragging is sort of like your select tool. And this is something I still haven't quite like gotten to grips with in KiCad, but like for example, if I want to move, say, if I move this capacitor out, it's all like well and good. It kind of extends this wire out here. if I select these again and try to move it back in, it starts putting this wire out to the side. It seems quite counterintuitive to me. I'm not really 100% sure why it does that, but it can also be a bit of a problem, particularly if you've got like a lot of parallel signals. I wonder if I can actually demonstrate this. Just draw a couple of sort of lines parallel to each other. Maybe it's not the best example, but if I sort of try and move this along, it sort of moves the whole thing like it. I'll probably need to have it actually joined up with some pins down here, but it's something to kind of be a little bit aware of, because it could cause you to move a bunch of signals and then potentially join a bunch of nets together that you didn't actually want to join. So it's something to pay attention to. It's probably not going to be a problem here, but if you're drawing like a schematic including a processor, some memory or something like that, it makes editing a little bit of a pain sometimes. To delete that bit of excess wire there, I can just hit like hover my mouse over it, hit the delete key, for backspace. And then actually, it might be a good opportunity now to sort of demonstrate the sort of how the mouse cursor works in terms of deleting things. So I'm going to put a couple of wires here, like on a 50 mil grid, and then I'm going to go back to 100 mil. So I can only sort of move the crosshair across the top and bottom ones. But if I move my mouse cursor over this wire in the middle, so the crosshairs move down to the bottom, if I hit the backspace key, oh, now it's going to make a full round. It is kind of like, oh, there we go. Maybe it's, okay. That's a different behavior to what I was expecting, but maybe it's because I was on a 100 mil grid. It sort of chose to delete the one that was on 100 mil before it deleted the one that was on 50 mil. Put it down here. It's probably not going to work quite the way I thought. Yeah, okay. No, it's making it cool. But there are some other, maybe it was the edit key or something, but yeah, I guess there are some things where I've noticed where it's not so much where the crosshair is, but more so where the mouse cursor is, that will kind of determine like whether you're editing something or deleting it. So yeah, that's something to sort of get used to and start playing around with it perhaps. All right, let's move on, keep this going. So I'm going to bring in a resistor which needs to run from VCC to pin 7, which is the discharge pin. I think I also then want a resistor in line with the variable resistor, and that's, I think, mostly so that if you turn the variable resistor right down to 0 to make sure that it's not just a short or dead short. So from pin 7 through those resistors into pins 2 and 6. And these two together. And then from the bottom here into our capacitor, which is going to go down to ground. And 5, just going to pull it up. Pin 4, the reset pin, looks like that just got pulled up. Q is going to be our clock output. And I can't remember what you do with this CV pin, whether you can just leave that disconnected or not. Probably doesn't matter too much, this is just a demonstration, but what I'll do is I'll just leave that one disconnected. I don't think it's too important, or maybe it has to be like pulled up or something, but with KiCad, if you have pins that you're not using on a device, you kind of have to mark them as not being connected. And that's done with this little symbol here, the no connection flag. So if you use that, you just place it on the pin, and that will kind of tell the sort of DRC and ERC that like it shouldn't expect anything to be connected to that pin. So it knows that it can kind of ignore it. So that kind of makes our clock circuit, I hope. Anyway. I'm probably going to need some more space. I'm going to change the size of the schematic sheet. And the next thing I want to grab is some flip-flops. So quite conveniently up the top here, we have our 7400 series in our library. And I'm going to go down and grab some 74 LS74s, standard sort of flip-flop. And the a lot of the things in here will have sort of like multiple units, I think they're called. So in this case, what we're going to have is like 3 units for this one flip-flop, and 2 of them are going to be the flip-flops themselves, sort of broken out individually. And then the final one is kind of like your power connections, so you can kind of just like tuck them away somewhere down here, out of the way. But just to make things easier, I feel bring them up here. And I'm going to select all of the 3 units and copy and paste a couple of times. And just get ourselves a whole bunch of flip-flops. Move these guys down away. And we'll sort of just sort of bustle the VCC and ground connections for them, maybe with some decoupling capacity if we're feeling fancy. And the last thing logic wise that we need is a XOR gate, which is an 86. Yes, it is. Okay, so we'll grab an 86, and here we're going to end up with a whole bunch of leftover gates. So I'm just going to place these all down here. So we got 4 gates, and then power supply connections. I want one of these gates up here with my flip-flops. So let's get all of these, space them out a little bit so I can place the XOR gate in the middle. Consistent with space. Yeah, there's that's sort of all of the logic I think that we're going to need. We're going to need a couple of other things though. So we need some LEDs. So I think I can go in here and search LED. It doesn't have a footprint, and that's something else I'll get to in a little bit actually, but not everything will come with a footprint sign. Let's see, we'll go with like some 3mm LEDs. Okay, so we can select the footprint right there when we add it. One of the things you'll kind of have to get used to with KiCad is that the schematic editor does not necessarily sort of, when you place a component, you don't necessarily place a footprint along with it. And a good example of that actually is probably going to be the resistors and the capacitors. They might not have any footprint assigned to them yet. But yeah, that's sort of something else to be aware of, because like example coming from Eagle, where basically each component that was listed in that sort of, when you're selecting what you want to add onto the schematic, every part that's listed is basically a part like as a footprint. So when you add that part, you're kind of adding the footprint as well. But KiCad is sort of like you add the schematic symbols, and then you need to like later add in like footprints to them as well. So we select an LED, we can select the footprint when we're adding it, and then we want to start placing it in. And I kind of want to Let's see. Yeah, so I kind of want to have. I'm going to sort of do like maybe a situation where I'm going to sink current through the LED into the flip-flop, just because I think it's going to make it a tiny bit easier to lay this out. The LED is sort of at the moment, it's kind of pointing in a sort of like right to left direction, but I sort of want to have this point in a sort of bottom to up direction. So if I hit the R key, that's kind of like rotate. So I can sort of, flip that around and make it, line up in a sort of better orientation for how I want to lay this out. And then I'm just going to want to copy and paste that a few times for at least the first maybe 6 flip-flops. So we'll have a bunch of flip-flops there, and then we'll have some sort of current limiting resistors for them as well. There may potentially only ever be one LED lit at a time, but it's also possible that if you want to really make things difficult, you might put a couple of bits into this thing and have the other person try to clear them out. So those are all about LEDs that will light up and sort of show where the bits are. And I'm going to leave the last 2 out just to kind of make them disappear, and so they'll reappear again on the left-hand side and start moving across. You'll have to be right on the ball to clear them out. A button, we're going to want a button for toggling with the XOR gate. So we'll add in a button up here somewhere, and I think we're going to need a resistor for that as well, just to sort of probably maybe hold that signal, maybe pull it low. And then you push the button, we're going to sort of pull it high. So we'll add in a couple of bits there like that. The LEDs are going to be supplied with 5 volts, and they'll get pulled down. Well, and that's another thing actually you might notice. And so when I selected all these components and then I just kind of started dragging it, you kind of see like I sort of started with my cursor in the middle here, but then as I started dragging it, it sort of moved to being focused on the pin. That's another thing that I kind of found a little bit annoying with KiCad, because it sort of, that's the whole sort of 50 mil grid thing. Like a lot of the components seem to be drawn sort of, assuming that you're working on a 50 mil grid. It'd probably be fine if I just worked on a 50 mil grid, but yeah, you might find that, and if that sort of happens to you, just sort of like, you just kind of need to keep your mouse as like centered as possible in the component to sort of prevent it from jumping off and sort of ending up somewhere else. All right, so that's, I think, a lot of what we need. Grab all this and move that in. And then we can start routing all of this. So I'm just going to, with this little square on the end here, I can kind of click on that and start extending that wire. You can also click on the little circle or the ends of the pins here to kind of, sort of draw wires in between. I'm going to do one more. And a little bit of space in there. Spacing out nicely. So we're just going to basically start chaining all of these flip-flops together. Nice and simple. This basically is just creating like the chain. So as the clock rises, it's going to clock whatever bit was sort of presented to each flip-flop into the next one, and then it's just going to keep moving way along. And then we need to basically return this all the way back to the beginning to sort of create the full chain. Then we need to make all the pull-ups together. Yeah. Pull-up. So everything will get clocked sort of synchronously, all at the same time. And that's sort of largely that. You've then got your set and reset pins. So these are sort of asynchronous functions of a D-type flip-flop. We're not really going to do anything. I'm not going to worry about sort of any sort of reset functions or anything like that. So what I'm just going to do is I'm just going to tie all of these sets and the resets just up to 5 volts so that they don't really do anything. But if we wanted to, and like I have in my simulation, we could add a button or something in to reset. Might actually be a good idea anyway. Yeah, let's do that. So we can add a button in to kind of pull the reset line down to ground. And we'll have a resistor in there to, by default, pull the reset line high. So that's kind of our reset sort of function. I guess if you, for example, if you were to apply power and like maybe all the bits were on, or there was a whole lot of random garbage in there, you could push that button. And that would pull the reset pin of all the flip-flops down and then clear them out. So it's basically like your cheat mode, sort of restart the game for function. We'll then tie all of the set asynchronous set pins. They'll just be tied high. You don't worry about them. Next, we want to do our button. So we're going to come right here. And we'll route that in. So what we have here is basically the input to this pin on the XOR gate is going to be pulled low by default by this resistor. And when we push the button, we're going to bring it high, and that will just invert whatever is coming in on the other pin of the XOR gate. So that's kind of going to be our way to inject bits into the game, and also the way that you play the game to clear them out. So that's all hinging around that. Right, so the last little bit of the schematic then is going to be to hook up all the LEDs. So we'll just leave one line here, and fill that up. Quite in alignment, but so that's all of our sort of 5 volt through our current limiting resistors. There's some weird mode about KiCad where it kind of knows that I was trying to hook things up to a 50 mil grid, so it's sort of remembering that for me. So that's like kind of make my job a little easier, but it doesn't stick and it'll come and go for some reason. But yeah, so now we hook our LEDs up to the inverting outputs of the flip-flop. So whenever for example, if the game is entirely cleared, maybe we've hit the reset button or all the bits have been cleared out, the Q output or the non-inverting output would be in a 0 state, and the inverting output would be in a high state or logic 1 or whatever, logic high. That would prevent the LED from turning on. But whenever it's sort of the inverted state, so whenever a bit is set within the shift register, the Q output will be logic high, and the inverting or not Q output will be the logic low, which will then allow current to sort of sink through the resistor through the LED into the in and turn the LED on. So rather than sort of using the Q output, and when that's high, we'll drive the LED. We're just going to use all the pins, and we'll just use this in sort of like a current sink rather than current source kind of arrangement. So finish. Yeah. Okay. And I think that's like pretty much sort of completes the schematic. And one of the things you can sort of do then is you can just start playing around with how things are kind of laid out. You can start to try and sort of create a little bit more space between things to sort of try and make it a little bit easier to follow and that sort of thing. A good point, actually, this is kind of a good demonstration as well. If I want to move this sort of thing here and sort of maybe tighten this little bit of the schematic up, I can sort of select the like the sort of 5-volt symbol there, and what would be it's sort of this wire coming sort of vertically here. If I try to move it across, you can kind of see how the wire on the resistor sort of now starts going off on a funny angle. One of those sort of little quirks, I guess you'd say, about KiCad. But if I just select this vertical wire here, I can kind of drag it along, and it sort of inserts this other bit of horizontal wire here. But then if I select the 5-volt symbol and sort of drag that along, then it kind of tidies everything up. So yeah, little things you've got to get used to with KiCad. Especially coming from another, if you've worked with another sort of EDA package, you'll have sort of like a workflow that you're kind of used to, behaviors and that sort of thing. And you might have to make a couple of little adjustments to how you sort of, how you work with things. So we have 2 flip-flops here where we have pins I'm not going to use. So I'm going to put the little no connect flag on them. That would be PLC happy with going this up. And I think that's about it. I think for the schematic layout, we should probably do something about these down here to give all of this power. So I'm just going to grab the 5-volt symbol here. I'll grab a ground symbol, put it down here. And I can draw slightly bigger symbol. Okay. Basically a little bit more. You can get quite sort of fiddly with your schematic thing, laying them out, sort of trying to make everything look nice and whatnot. So yeah. And maybe the last thing we should do, it probably doesn't matter too much. You can kind of get away with it with LS parts, but if you're using CMOS parts, you kind of want to pull any unused inputs down to ground or maybe up to VCC, so you don't have any floating pins. And then we need to chuck a little no connect symbol and outputs there. Okay, so crash course in drawing a schematic. The next thing to do, I guess, is going to be, well, we can go through and put values on all of these components, and that you could then potentially have it show up on your silk screen. To do that, you can basically just hover over component, hit the E key, it will bring up the edit window, and you just want to chuck something into the value here. So for a current limiting resistor for an LED, modern LEDs are pretty fine with 1K. At 5 volts, that would give you 5 milliamps, which is like plenty for a modern LED. We could sort of go through and modify all of these. Although what I'll probably just do is delete them and then just copy and paste. Or actually, maybe even what would be a better idea, if we go back in here, we might want to give this a footprint. So we can save ourselves a little bit of work by sort of, making a whole bunch of changes, and then we can just basically duplicate that first. So I'm going to find this roof hole, and then what I want is well, so you'll kind of see like a lot of this details about the footprint in here. So you have things like L 3.6 millimeters, D 1.6 millimeters. So these are like the length and the diameter of the resistor, and then you have P, which is the pitch. The pitch being the space between the leads. So like a prototype board, for example, might have 0.1 millimeter, or sorry, 0.1 inch, 2.54 millimeter sort of pitch between all of the holes. So for example, a 7.62 millimeter is going to be what, about 3 or 4 holes worth. I personally prefer to use like it's a 6.3 millimeter length body, which is kind of like your standard resistors that you've probably got on all sorts of boards around, retro computers and stuff like that. And a 10.16 millimeter pitch, and that basically, it's a lot of personal preference as well, but it means that when you sort of have to bend the leads to put your resistors into the holes, you're not having to bend them like right tight against the body of the resistor. You can kind of almost just hold the body of the resistor in your fingers and just kind of bend the leads over with the other hand, and then it'll slot in pretty much perfectly and even hold itself in place probably. But a 10.6 millimeter pitch, 6.3 mil body, and a diameter of 2.5, which is just like a standard resistor. So I'll select that as my footprint. I think double click will do it. Yeah, that'll put that into the sort of footprint field here. And if I click on OK, that will be assigned now. And then I can sort of copy and paste that with its value and its footprint assigned. Something else you can do, because I've got a few other bits and pieces here that I'm going to need to do. There is a tool to kind of make this all a lot easier as well. What do we have? Footprint assignment tool. So on this toolbar across the top here, there is a footprint assignment tool. And this is kind of like just a wizard. It's going to basically find all of the parts that don't have a footprint, and it's going to give you an option to sort of fill all these in. So I think if we just hit annotate down the bottom right, it's going to basically come up and say, right, you need to assign footprints for all of these parts here, which seems like quite a lot. But we can make this probably quite easy. I think we can select multiple, yes. So you can sort of select multiple parts to make this a bit easier. And then we're just going to look at basically, it's going to filter, looks like it's going to filter some, footprints that kind of would probably apply to this type of part. And looks like it's even got the one that I just used already selected. So I can, what was that? That was I've already assigned it. Oh yeah, so it's probably these ones here actually that I need to assign the footprints for. So I need to select the ones that don't have a footprint mentioned here. But we want to select like 6.3, 2.5 pitch of 10 millimeters. Do a double click. Okay, so that's going to fill them in. Push buttons, 74 and 36s. I think these can all be. Let's see. These are all like 14 pin. I think they're 14 pin. Yeah. Let's see, so we want a dip 14 with 7.2. We don't need to worry about anything to do with sockets or anything, but if we select probably that one, long pads will be the, rather than just being a circle pad, shaped pad, long pad will kind of be more of like an oval shape. So that maybe gives you a little bit more room to sort of solder to. So I might actually select long pads for these because they're quite convenient to solder on. Push buttons, right? Now this is going to be an interesting one. Where do the push buttons live? Push buttons. Switch home. Push button here, possibly. No, which one? 6mm kind of rings a bell. Let's just use that. We can always change this later as well if we sort of find that maybe a footprint is kind of doesn't really fit, or maybe we've got some existing parts in our stock or whatever, or there's some particular thing that maybe it's the only one you can buy from your supplier. You might have to change the footprint, but that's fairly easy to do. So we'll just go with that for now. Capacitor. We're going to go with through-hole capacitors. Take some radials with a pitch of 10.5, diameter 12, and that's 6.2. Maintenance, disc. Okay, we'll just choose some sort of disc style capacitor, like a little, typical sort of orange little ceramic capacitors, and we'll have a pitch of, let's just say 5mm. Doesn't matter too much. All right, so that should be now all of our components assigned with a footprint.
Tom, I think your variable resistor has a dip footprint.
That'll do it. Yeah, actually, you're probably right. The variable resistor, where is it? Okay, something that, 103. Yeah, that was okay. Okay, so we need to find a variable resistor, which probably potentiometer through hole here. This is potentially a little bit nicer way, maybe to find like the footprint for perhaps the first part, because you can actually see what the footprint is over here. Whereas before, when we were using the footprint assignment tool, you can't actually see what the footprint is. You don't know, the shape of it, how it looks, anything like that. So we just need like a standard kind of looking little potentiometer footprint, something like that, maybe. Yeah, we'll go with that. Okay, that's probably a bit better. And then we can also see actually that it looks like as part of the annotation process, it's actually added all the component designators. So R101, U101, etc. We can change that if you want. Like that's probably just left over from something that I've been doing. But if we click on this button up here with the R question R42, which is the what's that schematic symbol reference designators, we can sort of change that. So I've got it kind of doing like per sheet, it will kind of do it in blocks of 100, but we can change that to if we just leave it up to first three number up to 0, we can sort of re-annotate the schematic, and now we have things like U1, R1, C2, etc. So if you've got multiple sheets, for example, I've seen it on some circuit boards where you might have a power supply section and all of the components around that are kind of like, they look like they're in one group of numbers, and then you have another section of the circuit board where all the component designators are all kind of like in another group of numbers. So that's kind of like that, what that sort of function is. So, on a per sheet basis, you can kind of, either do it in groups of 100 or groups of 1,000, something like that. Or you can just use, the first free number after some value, because you could, for example, you can keep the existing like designators that have been assigned if you want. So rather than sort of going through and like completely resetting the whole thing and renumbering everything, you might just choose to sort of say, right, well, I was up to D6 or something for my LEDs. So the next one, I might want to label after D6. So I might want to say like use the first free number after 6 if I add another LED or something like that. So you can either keep everything or sort of reset everything and start from scratch, which might catch you up a bit. For example, if you write notes and you've sort of documented, like place a jumper on J1 or something, and then you sort of you add another header or something on another sheet and then reset everything, and then all of a sudden all of the documentation is now out of whack. So that's something to keep in mind as well. It looks like you can change the direction in which it sort of assigns the parts. So in this case, for example, would there be a good example? Yeah, so like here we kind of have like R1, R2, R3, and that's kind of going in a sort of top down sort of direction. But if I go in here and change the order in which it sort of allocates numbers and then reset everything, and we go back over, and now we can see we've got, well, R1 I guess was higher vertically in the schematic than R2, but now we have R2, R3, R5, as it's now sort of allocating more so in a left to right, top to bottom direction, rather than top to bottom, then left to right. So yeah, that might be something that you sort of just need to play around with and see if that kind of produces the results that you want. And you can obviously do that just for an individual schematic sheet, or you can do it over the whole thing, or maybe just select a bunch of components and rename them. So that, I think, now should be the schematic complete. You can save that so we don't lose any work. I have had, I don't know if it's just my laptop, but I have had a couple of crashes with KiCad. So yeah, probably best to sort of save your work, frequently, as a good practice, maybe. Okay, so any questions from anybody so far about the schematic side of things? Because I did sort of run through that quickly.
Could you demonstrate using a bus, so a set of wires? Yes.
Okay. Good idea, because I know you were interested in that from the discussion last time. Yeah. Okay. Let's put the LEDs on a bus. So I'm just going to delete out all of these down here, and then I'm going to try and sort of fix that up. Yeah, and then I'm going to kind of all this. And put all the LEDs very nice and tightly together. And I'll move them down here where they're completely out of the way and unassociated with anything. And then I'm going to draw a bus. So a bus is this big thick blue line over here on the right hand side, and you kind of draw it just like you draw a normal wire. So you just sort of click on this tool, and I'm going to start down here, and I'm going to start one across, and I'll get to why I'm going to do that in a moment. But I'm just going to draw a bus, and then I'm going to come around here, and I'm going to stop one short. So drawing a bus onto your schematic is like literally just like drawing a regular wire. There's nothing really special about that in particular. You don't have to give it a name, I don't think. But you, to give something a name, you actually would use these little things over here. So you've got your, what's this, net label. You've got a global label, and you've got a hierarchical label. A net label is something I'm going to use when I label all of the signals coming out of the flip-flops. A global label and a hierarchical label, these probably really only make sense if you're going to have multiple sheets. Although you might prefer the style of a global label over something like a net label. I might just try and use an example. So coming out of our 555 timer, I'm just going to use the net label tool, and I'm going to call this clock. And then I'm going to like basically click on there, and then that like has basically just given actually another hotkey is the tilde sort of backtick key. If you push that, you can highlight net. So I've given this net coming out of the 555 the name clock, and then I can use the little backtick key, kind of highlight that, and then I can see, you know, at a glance where it's going. But what I can also do, if I really want to, is I can come down to say like here somewhere. I can put just a piece of wire down here, and now I can either put a net label on it. If I just remove the highlighting, I can highlight this. So I've highlighted that clock line, but if I come up here, I've also highlighted this because these two nets have the same name. They're not physically connected or anything, but like that's one style of label. Another style of label is with these global labels, which kind of come up, they look more like a flag. So you can kind of put, you know, a little flag like this on as your net label instead. You know, it's still the same, achieves the same goal. You know, you've got, they're both, you know, logically connected because they have the same name, but it's a different sort of style of label. And you can also change kind of like how it looks. So in this particular case, the way that it's kind of oriented is sort of, if you think of like a schematic where like kind of all of your inputs come in from the left and all of your outputs go out on the right. So with this label kind of pointing to the right would sort of suggest that it's an input signal. And indeed, if we sort of look here in the properties of the label, we can kind of see that it's specified as an input. If I change that to an output, rather than the sort of arrow pointing into the signal, it's now kind of pointing out of the signal. So this is actually something that I really like about KiCad, because in Eagle, all of the labels kind of look the same and they all look like this. So whether they were inputs to a schematic or outputs or whatever, they all look the same. But with KiCad, you can actually stylize them a bit more. So I tend to focus more, like especially if I'm just, if I need to have like signals and it's a really busy schematic or something, and I want to like organize things a little bit with, you know, some labels, I'll tend to use these global labels, even if it's staying on the same schematic thing, just because it looks nicer. But you can also change it to be a bi-directional, you know, where it's kind of like got both ends of it are sort of, you know, stylized to look, you know, to make it look like, you know, or indicate that it's sort of input and output. Let me translate before that. Translate with nothing. Okay. That's it. Okay. Yeah, it's some different styles of labels that you can apply. The hierarchical one is sort of it applies when you have like multiple sheets. could even maybe we'll do it afterwards. We could add a sheet in and like move all of the LEDs and stuff onto another sheet, and then we could use, for example, a hierarchical label. And that's I think they sort of help most when, say, the top sheet is kind of like just a series of other sheets that you drill down into. You can use the hierarchical labels for inputs and outputs, and then like within the sheet, and then in the top sheet you can kind of add little connectors for inputs and outputs onto the little sheet icon, and then you can kind of draw like a really, really high level sort of schematic, which is kind of like just how all the different modules connect together. And then you drill down into those modules and you can see how the actual circuit of that module is sort of made out. So that's I haven't done too much work with that sort of stuff, but yeah, it's kind of nice. But anyway, back to the buses. The reason that I sort of stopped one short here from lining this up is because you've kind of got like a nice little stylized bus entry / exit sort of tools that you can use. So you can add a wire entry to the bus, and basically all it is like a 45-degree angle piece of wire. You could draw this by hand as well, if you wanted to. Like by default, KiCad sort of constrains you to right angles only. But for example, if I go up to preferences and into schematic editor, in editing options, I can remove this constrain buses and wires to horizontal or vertical. If I take that off, I can then draw a line, wire on any angle that I want. So that sort of includes like drawing entries and exits for buses. There's nothing particularly special about the bus entry and exit tool, except that it kind of just gives you a way to just sort of plonk down 45s wherever you want to, enter and exit the bus. So there's nothing special about it. And then, once I've drawn them, I can sort of just, join everything back up again. So that's kind of how you draw signals going into a bus. So far, there's nothing really special that's been done. The last little bit, I just need to finish off this. It's basically just going to be labeling the nets, and that's kind of how you're going to make it all work, and that's where the magic is going to come from. So
right.
We've drawn all of our flip-flop outputs connecting into the bus. Yeah, that's doing that. Okay, maybe that's because of the wire. Maybe that's why you have the bus entry tool. Okay, so a wire kind of seems to leave a little bit of an end on there. Okay. So we've got all of our outputs from flip-flops, we've got all of our LEDs, and now we kind of want to make the bus kind of actually function, I suppose you might say. What I'm going to use the net label tool, and I'm just going to say, let's just say, one thing we can also do actually. So we can call our signal LED1, and we can place that on that signal. But I guess you could say in theory this is going to be active low logic, and we all know that like active low signals kind of have a bar across the top of the text. So what you can do to put that little bar in, I believe the format that I found out was like a tilde, and then you use the wiggly brackets around the text, and then that will give you the bar across the top of it. So that helps you sort of visualize that it's actually active low logic or signals. But you can sort of do something like this, where like if you had, for example, like a 68,000 with the read write signal, you only want the W to be sort of stylized as active low, so you can kind of just put some text, before and after, and you can sort of turn the that bar sort of stylizing on and off based on where you need it within the text. So yeah, we can copy that label and go down here and chuck it here as well. If we, for example, highlight this net, it doesn't know anything other, like that's its own independent net, and this one and this one and this one and this one. And likewise down here, these are all different separate nets, but this one here where we put the LED1, or we put these labels on, I can then highlight this net and we can see that they're now connected. So that's basically like a bus, is you just sort of draw the line, you then draw entries and exits, and then you label each of the signals on either end, or as many entries and exits that you've got. And then I can duplicate this label across all of these nets. And then I just go through and change them. One of the things you can actually do is you can use the arrow keys as well. KiCad seems a little bit more friendly with like keyboards type. If you're a keyboard person, then you can just use your arrow key.
Down there.
Scroll around.
Select down there.
Somebody not muted. Yeah, so we now can see that through labeling all the nets, we can now highlight them, and each of the two ends will sort of highlight together. And yeah, so that's basically how you do a bus. The bus itself doesn't really know what it is. I think you can put labels on it, particularly if you're going to route it off to another sheet in a schematic. Yeah, so if you need to have like an address bus and you're going to have that spread across multiple sheets, then you could chuck a label onto the bus itself. It looks exactly the same as any other label. If I just put that out there and then say, I'll just call this the LEDs bus. And I'm just going to chuck that there. Like that's labeled. So now if I had another schematic sheet, I could start drawing a bus on that other sheet, give it a global label called LEDs, and then those two buses would be connected together across those sheets. Yeah. Same deal, like if I was to highlight it. So yeah, so there's our schematic for the game with a bus now as well, a good measure. The next step, I guess, being wary of the time, would be to start laying out the PCB. So to get to the PCB, you've got this sort of little icon up here on the top bar. It kind of looks like a couple of traces and conveyors. So you click on that, and that will bring you into the PCB editor. And kind of looks a little bit in a way like the schematic editor. You've just got a sheet here, but there's no components on it. So it's like, how do you get all the components into your schematic? Well, that's this button up here, which is basically update PCB with changes made to the schematic. Looks like you can also press the F8 key. So you click that, and basically what it's going to do is, well, it's going to tell you here what it's doing. So it's like adding all of these footprints. But if we hit update PCB, oh, okay. I thought it was going to go away on me. Here basically are all of our components now. I can just sort of tuck them off to the side because I don't want them in the way just for now. And what we need to do now is basically start drawing or placing all of the components and then sort of laying out how we want the board to look physically. And how do I do this again? Yeah. There is a particular layer, I think, that you've got to draw the outline on. It might be B fab and or F fab and B fab. Might be. Anyway, what we want to do, I guess, is we want to maybe roughly size up, how big the PCB needs to be. But we need to kind of draw in the actual outline of it first. Okay. Right. Anyway, I'll just have to keep going. I can't remember exactly which layer it is, but one of these layers here will kind of allow you to define the actual sort of dimension of the PCB. And I thought, unless I'm just blind, I thought there was a layer called dimension. But it might be something like these fab layers. You might just have to draw it on both of them. Yeah, maybe I'm gonna have to have a look at another schematic or another PCB that I've drawn and see what layer it's on. For now, I'll just use the margin layer because it'll be nice and obvious. But what I can do is working in millimeters is quite nice. So if I select the millimeters sort of option over here, this is kind of like a radio group between inches, mils, and millimeters. So if I select millimeters and then go up the top here, I can select the grid. And it's probably going to be easiest just to draw it on 1 millimeter grid. So I'll select the 1 millimeter option, and then I can draw in like just for 12 by that much, say 12 by 7. Oops. So we'll make that the size of our PCB. It's probably going to be big enough. And then we can start moving some components in. So let's start by selecting the 555. That's in there. We'll go label resistor and something you might need to do every so often is, well, you can either use the air wires to kind of guide you into like what components are sort of associated with each other. Some labels. Or you can sort of jump back and forth between the schematic and the PCB. Like, so in the PCB editor, you get this option here, or this button, which kind of looks like the schematic symbol. You can click on that to jump back to the schematic. And in the schematic, you can click the PCB icon to jump over to the PCB. And what I'm sort of wanting to do is I just kind of want to figure out what components are associated with 555. So it's C1, R1, R2, R3, C2. So I can then go over here and kind of maybe even just do like a little bit of sorting. So just 1, 2, C1, C2 here. So these are all my 555 components. I can start laying these out. You can use the R key again to sort of rotate things. Basically, all I'm going to do is really just position these components you know, just so that the air wires kind of look like they're so the air wires are kind of laying themselves out in a like a way that's going to make it easy to kind of route all these traces. Do something like that. That wouldn't look too bad. Probably do that on 2 layers. We've got 2, 3, 4, 5 flip flops. We'll grab these, place them. Those are all the flip flops. What I might do is potentially actually move those and stick the XOR gate in the middle of them because they're kind of related. A little bit more. So those are all about chips place. We have something that's going to be a reset button. The reset button. So that's going to be our reset button. I can actually give this a name as well. So rather than being switch 1, we'll like reset. And then if I go to the schematic and just sort of update. Not one. Do that. Oh, it's going to call it reset. But at least I can see that, you know, that's the reset button. You could also place that on the value. So maybe change that to question mark reset. I can see now that that is called reset, but this may not appear on like in the Gerbers if you, for example, don't turn on the fab layers. If I turn off the fab layer, which is sort of can be more documentation rather than actual, you know, sort of things that you want to appear on the silk screen. But you could, if you positioned everything correctly, you could in theory place the fab layers in the silk screen as well, but I don't tend to do that. It's usually got like part numbers, all this sort of R variable stuff, like the values and stuff like that. You may or may not want those on your silk screen, for example. Oops. You want a button in here somewhere. Put that in the bottom corner there. And here. What are you doing? Right, I might try something. Maybe it's selecting like a piece of text or a pad or something. So you've got this selection filter down in the bottom right here, and I can say I only want to select footprints rather than like pads or text or anything. And that might help me to kind of, you know, better select the middle of the component and not coming to ironically select a pad. Use that to place things out. Something like that. That board already do. Position of these, so associated with the reset button. Here, associated with the other button. This button, and then these are probably all the ones associated with the LEDs. So they probably be in order 6, 7, 8, 9, 10, 11. A bit more. I'm sort of rushing a bit now because it's a bit aware of the time. If you were doing this like, for real, you might sort of want to, you could spend days like just fiddling with the schematic to sort of, a PCB layout to make everything look, really nice and proper, and everything properly lined up and spaced correctly and all that sort of thing. So got a bit, rough PCB layout there. Happy with it, something you probably should do before you start placing components really is like positioning mounting holes and stuff like that. Because the worst thing that you can do is like lay out a PCB and they go, now how do I like mount it to anything? How do I screw it down? How do I, stack it together with a bunch of other boards? So ideally, the first thing you want to do is position mounting holes, and I think you know how to do that. The footprint. So this little icon, it looks like a chip. If I search for mounting or mounting hole, I can sort of get, I can choose from a bunch of different holes here. So I'll choose 3.2 millimeter for an M3 screw. And then I can just position some mounting holes in the corners of the PCB. And that would sort of give me now somewhere that I could, like screw this down onto wood or something if I wanted to. But ideally, you do that first, because then if you had to fit all of the components onto a board, you would be able to, you would know what your sort of limitations are. Like, you can't put things right down in the corner here because you need to leave some space around the mounting hole to for PCB stressing and that sort of thing if you screw it down. So basic sort of very quick rushed sort of positioning of components. And I guess the next step would be basically to start routing things. But one thing that I kind of never really cared about much, but when I started using KiCad became a thing that I did start caring about, was its 3D viewer, which is quite neat. If you go up to the view menu and go to 3D viewer, you can get a 3D rendering of your PCB, which is really nice. You can sort of look at it and see how everything is kind of, positioning and roughly how it's going to look when you get it produced. Something not quite right with my dimensions, because those should have been right in the corner. But yeah, anyway. So that's, a nice little feature. If you've got a very big, busy board, it can look, quite interesting. So let's start routing some traces. In this case, we're probably going to be fine with a 2-layer board. You might, with a bit of work, you might even get it onto a single layer. 2-layer board is basically the de facto standard now for, like, all the cheap Chinese manufacturers, like the price of a 1-layer board is probably exactly the same as a 2-layer board. So you might as well just go with 2 layers and give yourself, some extra options for routing traces. It's very common for traces on one side of the board to be routed in one direction and traces on another side of the board to be routed in the other direction. And that can help you to sort of achieve like quite complex designs on, maybe only 2 layers of, signal layers in particular. So we can just start fiddling around. So I'll start by selecting over here the bottom copper layer. And to route some traces, you just select this sort of this icon here, route tracks. You just click on that, and basically you just start clicking on in between pads. So let's see, I'm going to go to a smaller grid as well. For routing, I tend to use mils. I don't know why. It's maybe like a bit of habit or something, but I might go for something like 25 mils, which is going to work quite nice for routing in between through hole like dip pads and stuff like that. So I'll just start routing traces basically. Here, in between. So probably things like power supplies, you probably want to do with some thicker traces, just for like current handling capabilities and stuff like that. For signal traces, I think what are these set to? So if I just edit one of these traces, you have to select tracks down here to be able to edit the track. So this is a roughly a 10 mil trace, which if you use a lot of sort of calculators online, a 10 mil trace would probably tell you that it can handle, I think, about an amp of current, which seems crazy, but yeah. Four is so pin 4 is just a signal trace, so I can maybe have this come straight up. Pick up from the power supply. So that's most of the 555 sort of routed out. We can do this button. This button over here. I'll just do that. They will all get routed together. All the 5 volts. And the last one, first. This is all going to be fairly similar, so I can sort of route, just route and repeat, kind of try and make everything sort of look the same. this is not my best work. If I was a little less concerned about the time, I would spend a lot more time to make this look much nicer. So I'm trying to get it all completed. Hopefully, leave some people with some time tonight. Okay, so here we've got an interesting little situation. We've kind of routed ourselves into a corner. So we've got the clock output pin here, which we want to get over here. So far I've done a lot of stuff on the bottom layer, and at some stage I do also need to get, for example, these traces across here. So I'm just going to like jump up to the other layer to route these traces. So go across, across here like so. What is going to send across the board. That's our clock to everything. These are probably just the resets. They're going to need to keep this up to pass that. And what have we got? Let's go back to the bottom layer to these traces. Probably something to do with the shift register chain. All the way back in. This one, a big long journey. All the way back in here. That was probably the shift register chain. Now, what else have we got? This is the output from the XOR gate, so that's sort of feeding back into the register chain, maybe. We might need to put some stuff in another one. So all of these pins which need to be grounded. What I can do is I can ground these in the top layer. And then I'm going to go to the bottom layer here. And top layer. I'm sure you'll kind of get the gist, because I think I'd like to probably move on to the Gerber part of it. But this is sort of, you know, the general idea of it. You know, you can use these air wires here to kind of guide you about, you know, what needs to connect to where. In particular for like logic gates where you have like, you know, maybe 4 gates in a package. When you're laying out your schematic, you know, for example, I just chose, you know, gate A, you know, because it's the first one or whatever. But as you're laying out the board, you might sort of decide, oh, you know, like, well, maybe these signals, rather than having to try and route them up to this top of, you know, top corner of the package, you know, maybe it's better if they're down on this part, you know, and that's where you sort of get into it's a process called gate swapping, where you kind of shift things around. You can also do pin swapping, where maybe instead of having these two signals route, output of this pin into this pin and that pin to there, like maybe you swap. That doesn't work here, but maybe you swap some pins around, and you can do that just to kind of help with the layout. So things like if you're routing a PCB with a processor and memory and stuff like that on the board, particularly for RAM, it doesn't matter if like D1 of the processor goes to D1 of the RAM chip. The RAM, whatever you write into it is what you're going to read back, because if that's the way you wire it up, it's fine. A little bit different when you have something like an EEPROM or a flash memory or something, because the bits that you write into that, need to match the, what the processor is going to read. But it's entirely possible, for example, to wire D1 of the processor to D6 of a ROM. You'll just have to make sure that you shuffle all the bits around for each of the bytes to match what the processor is going to read out of the ROM. But you could certainly do that to help you with, if you wanted to try and, for example, achieve like a single layer routing or something, you could certainly move things around, just to make the routing of the board easier and keep everything, flowing. And there's a guy on YouTube, Mike's Electric Stuff. He has an example of doing something like that for a product that he built like way back in the day, where he basically just routed all of the like data and address signals the most convenient way for a single-sided layout. And then when it came time to writing the software, rather than just programming bytes literally into the ROM, it was more like, well, write a script or something to kind of shuffle all the bits around and kind of move chunks of code to different spaces based on how the address and data lines were done. But that meant that everything coming out of the processor just came sort of straight out of the processor. You didn't have to do lots of jumping over to line signals up and stuff like that.
Question. Is there any auto routing facilities inside this tool?
I think there is. It's probably one of these options over on the left-hand side here. I personally have never used it, so I don't actually know where it is. Maybe up here. Interactive, that's what we're using. I believe that it has an auto router, but I've never used it, so I don't actually know how you start it. It's a good question. That's something we'll have to probably look up, because I don't actually know where the auto router is.
Yeah. And are you restricted just to 2 layers of metallization?
No. So if we go into, I can remember how to do this. It's in here somewhere. Let's see, edits.
Hold on. Yeah. You do have buyers.
Yeah. Is board setup maybe? Yeah, that's what I'm looking for. So board editor layers, physical stack up. Here we go. So this is where you can select the number of copper layers you want. You can go all the way up to 32 layers. But you can also, through here, you can modify the thicknesses of all of the different sort of dielectric layers and stuff. So if you go to a 4-layer board, you've got you can put in the thickness of the like the top layer copper, the dielectric thickness, what type of material it is, whether it's core or prefab. So if you were doing like a very high speed design and you really needed to worry about impedances and stuff like that, you can come in here and you can like set up all of these parameters. So like, if you go to like an 8-layer board, you're going to have a lot more dielectric layers and inner copper layers and stuff like that.
Right.
To work with that. And F is your sort of top layer or maybe front, and then the bottom layer is going to be B, and then you just have like all of the inner layers, which are just like in, it's like in 1.cu, the copper layer, in 2, etc. I'm not happy with that. Okay. So where did I find that? File, board setup. It might be slightly different on Windows, I don't know. Especially, particularly like the preferences, like it's a very Mac thing to have like a menu named after the application, but that's where I find preferences, and that's where I find all the different little settings for like colors and stuff like that. Yeah. So that was a bit rushed, but what I'd like to do now is probably go to, like, I haven't finished it obviously, but is generate the Gerbers and show how to do the PCB order. So what do we do?
Oh, sorry, Tom. Just to answer John's question, it sounds like there's a separate tool called free routing, which you can use to do auto routing for KiCad.
Yeah.
Rather, it doesn't sound to be something built in. I think.
Oh, okay, all right.
I think it's a separate application.
I would have assumed there was something built in, but yeah, there are a lot of plugins and stuff like that as well. So yeah. But actually, we'll have one last little look at our PCB now that we've got some traces on the board. You can kind of see them here in lighter color. Up here on the top bar, you've got some options to turn off all the components, and then you can sort of get a bit of view of what's going on underneath all the components, and you can flip the board around to the back side and have a look. And there's all these other options, I think, just for like doing certain modifying your projection and whatnot. But you can also just grab with the mouse and just kind of flow it around. So yeah, components back on, and you've got like through hole and surface mount components. We don't have any surface mount components, so clicking that button does nothing. But yeah, we can certainly turn off the through hole component. Right, the Gerber process, I think, is file exports or fabrication. Probably yes, fabrication outputs Gerber. So here, you sort of select, I guess. Not right. Been a while since I've generated Go. Thought there was a way that you could sort of select what you kind of group different sort of things. Like, so for example, you've got your F silk screen. You might want to sort of group multiple sort of layers onto one sort of output. Or am I confusing it with eagle? Let's try generating some Gerbers. Let's go through folder. Actually, before I do that, JLC PCB has on their website some instructions on how to output the Gerbers specifically so that like it's more friendly for them. So how to generate Gerber and drill files in KiCad 6. And I'm using KiCad 6. KiCad 7 is out. I haven't really played around with it much yet. So this will sort of guide you through how to set all the different options to generate Gerbers that will be more friendly for PLC PCB. So it kind of looks like it wants us to select a bunch of layers, so like front and bottom copper, edge cuts, right, that's what I'm looking for. That was not a layer, oh, it is a layer. Oh, yeah, that's what I was thinking of then. Right, so edge cuts was the one that actually defines the outline of the board. If I want to modify that, I just need to select graphics because I've kind of deselected it, but I can edit this box that I drew earlier on, which was on the margin layer, and I can change that to edge cuts. And it changes color because now it's on a different layer. And if I look at the 3D viewer, it looks a bit better in terms of the dimensions now not exceeding further out here. So file, fabrication output servers. Things that it's sort of, well, things that we will need to include here. Front and bottom copper, because we have a 2-layer PCB. Front and back adhesive, we don't need to worry about them because that would be, for example, if you needed to place little dabs of glue to like stick down surface mount components, maybe for a wave solder process. But we're not going to worry about that. Front and bottom paste. That is if you were doing a surface mount board and you wanted to have a stencil created so that you can squeegee on your solder paste, that would come from these paste layers. And that basically what it does is it just has little markings where all the surface mount pads are. So those are the things that would get cut out from the stencil. And those are where, like, you know, when you start squeegeeing the solder paste on, it would go through those holes and stick to the board. But we're not doing anything surface mount, so we can turn off those layers. The front and back silk screen, things like this text, like U5, D6, R11. We can also put our own text on there, like, you know, you might put the instructions on how to play the game, or put the name of the game, or whatever product. You can also put like graphics on there if you can sort of load them in. But yeah, so we can have front and back silk screen. I don't think you pay anything extra to have silk screen on the front and back of the board, especially if it's a 2-layer. Like, so you might as well just include them. You can put more text on each side. The front and back mask. So the mask is all of the silk screen like apertures, like around pads and stuff like that. So if you don't include the masks, you'll probably find that all of your pads come back with solder resist, sorry, I should say, over them. So you kind of want to include the masks because that sort of tells, like, for the PCB manufacturer, like where all the pads are, how much you know, still solder mask should be left off around the pads. A lot of the times I actually suggest to use like 0 what do they call it, expansion, I think, and then they will actually like expand the solder mask away from the pads enough to meet their own sort of tolerances. So you can say, like, you know, around a pad you might want like a tiny little bit of expansion so that, you know, any slight alignment errors don't cause the solder mask to kind of go over the pad itself. But a lot of the manufacturers will just say, like, just leave a 0 mil or whatever expansion figure, and then they will expand the solder mask to meet their own tolerances. Edge cuts obviously was our dimension, so that's quite an important one because that's how they know how big to make the PCB. And drills are not included in the Gerber. That's a separate file. So all of the holes for, you know, the pads for the through-hole components, the mounting holes, those will come from a separate file. So for us, I think all of these layers here are perfectly fine Gerber wires. This will also kind of tell you what other options to select or deselect. So what reference designators, we don't want values, you can put them if you want. Protel file name extensions. Check zone field before plotting. Coordinate format 4.6. None of these options here. So we then click plot, and that will generate the Gerber files. We can then click generate drill files. And then the drill files we have to do separately, and that will be Exelon format, use alternate drill mode, Gerber. Drill origin is absolute. Will be millimeters, decimal format recommended, that looks fine. Output folder will select the same folder here. Where did that go? Oh, I see what it's done. Okay. Anyway, generate the drill file, so that's done. And those are the only two steps we need to do to kind of produce the manufacturing data. So now what I can do, I can find it. Where would it be? Documents. I can have 6 projects. Here's a bit. Here's a bit. Unfortunately, they didn't end up in the Gerber's folder like I wanted. But that's all right because I kind of know what they are. So Gerber layer, drill files. Yeah. I think those are all the files that we need. So GTL is like top layer, GBL is bottom layer, GBS is the silk screen. What is that mask? GBL is silk screen. Front and bottom silk screen, front and bottom copper, front and bottom mask, plated through holes and non-plated through holes. So for example, the mounting holes are non-plated, so they won't have any copper through the middle of them, whereas plated through holes will. So all of the pads for components, for example, they'll be plated so that they connect the pads on the top and the bottom are connected through. So I will zip all of these files up and then we'll go over to pcb.com and we're going to order some boards. And the good thing is that you can basically just upload the Gerber file and it will kind of work out all of the layers, like how many layers you've got, the size of the board, and stuff like that for you. We'll go to the project, select that, we'll upload. It should give us a little preview of the board.
Would you also normally have a connection for the power and ground?
Yeah,
terminals?
just kind of left that out for brevity. I think there's also some little flags that you need to put in. They're called power flags. So I didn't add them in because I was kind of trying to make sure that I didn't go too long, but it's called a power flag. And I think it's meant to designate a particular net as a power supply. I need to look up again exactly how that works because I can't quite remember, but I think you need to put that power flag on it, like at least somewhere on a net, if it's going to be a power supply. So, okay, so here it's actually given us the front and back now, so I've changed that since I last ordered the PCB, but it kind of gives us a quick little overview of what our PCB looks like front and back, so we can make sure that, for example, we can kind of see that we have all of our silk screen on the front, that we have some traces on the front and the back. Anything that was on there, I think you can also use the viewer. It's going to make me log in. Okay. Again. And then I'll start running through the options. So FR4 is your basic standard PCB material these days. It's like fiberglass. Comes in however many layers you need. For something like this, you don't need anything particularly fancy. Like when you start seeing things like Rogers, this is when you start getting into like impedance controlled stuff. So like if you're doing super high speed signals, gigabits per second, whatever, you're going to be looking at probably some, Rogers board that's going to be incredibly expensive because it's like incredibly like impedance controlled. But for us, very simple board, FR4 will be fine. Here we can select the number of layers. 1 and 2, I believe, doesn't really change the price. No, 720, 730, okay, 10 cents more. But once you start going up to like 4 layers, and anything beyond there, 6 layers, you start getting pretty expensive. But when you start getting to these higher layer count boards, you're into a different sort of territory there. Like there's a lot more manufacturing that goes into something like that, and making sure that all of the layers line up correctly during manufacturing, and like when you're drilling all the holes and stuff. So yeah, the price goes up, quite considerably, which is a bit annoying because I'm working on a project at the moment, which I think is going to need to be a 6-layer board, and I'm already looking at the price of something that's a lot smaller than what mine's going to be. So yeah, that's expensive. So it's already picked up the dimensions for us, which was 120 by 70 millimeters, which is exactly what we drew in the PCB editor. The minimum you can order is 5 boards. I guess that's just what they do, but it looks like you can, basically order up in, lots of 5 until some point, and then it's, 10s and 20s and whatnot. It probably does get a little bit cheaper per board the more you order. But yeah, I guess it just depends on how many excess you want to have left over. Like one of these boxes up here is like full of PCBs that I've designed, and now have like 4 left over because I only needed 1. But yeah, minimum of 5. But you can see here that the actual boards themselves are only $3. And that's $3 for the 5. So we're talking 60 something cents each, 66 cents. A little bit of an engineering fee, which I don't really know what that means, but build time will be a couple of days. And shipping is the thing that kind of really sucks in a way, because it can easily double or more the price of your order. So what are we? We're an industrial or consumer or products. We only have a single design. They can get a little bit picky if you try and sneak multiple board designs into like one order. Sometimes they'll look at it and they'll come back and say, oh no, you need to pay a bit extra because actually you're ordering like 2 different types of board, and like somehow just kind of join them together, and you're going to separate them yourself. But yeah, if you tell them how many designs in there, maybe they're a little bit less picky about it or something. You can sort of select whether you want to receive, just individual PCBs that are already cut out, or you can receive them in panels. For example, if you're going to produce something on a, like a pick and place line, you might want several boards panelized so that you can send them into a machine and it will, you know, sort of populate several boards at a time, and then they'll go into the reflow oven and solder several boards at a time. And you can either do that where you specify the panelization, or JLC PCB will specify, will sort of panelize for you. PCB thickness, so basically just how thick is the PCB going to be. 1.6 millimeters is basically the standard. We don't need to change anything to do with that. It will probably get a little bit more expensive if you go to some other thickness. 1.2 is fine. Millimeter is fine. 1.8 is fine. Okay. No, there we go. So it looks like most of them are about the same price, and it's only if you go to something really far out. Obviously, like a 2 millimeter board is going to be like a lot thicker. It's going to probably be a bit more rigid, and certain other things, you know, you might need a thinner board for. Color. I think you can have any color you want. What does it? Looks like it does. Yeah, green is kind of like your standard and cheapest. So let's finish one of that. Oh, yeah, looks like we can have any color we want. Yeah, so choose whichever color you want for your PCB. It looks like you get a little, that's a very Osh Park style PCB there in purple, red, yellow, blue, white. White's pretty typical if you're doing anything with sort of like LEDs, black. Silk screen color looks like pretty much on it's white board, and you get black. Surface finish. So this is basically what the PCB is going to be finished with. So ENIG is kind of like your gold plating. You just sort of have a board here, sort of, you know, that's kind of got an ENIG coating on it, which gives it like a gold color. It's not hard gold though. So like JLC PCB doesn't do hard gold. So hard gold is kind of like your edge connectors. Yeah. So like that's like an ISA prototyping board. ENIG is a very soft gold, but it's good for like in terms of surface like flatness. So if you're doing BGAs and stuff like that, typically it's recommended that you get an ENIG finish because the surface will be a lot flatter. Hazel is basically where they sort of dip it in like solder, and as they extract it out, they kind of blow air over it to sort of blow all the excess solder off, and that's where you kind of end up with everything, like all the pads that kind of look tin. And then you've got the option between like leaded or lead free. Annoyingly, lead free kind of costs a little bit more, but like I've ordered all of my boards in recent times with lead free Hazel, or most of them anyway. Just, you know, trying to do my little bit for the environment. Copper weight is basically how thick the copper is going to be on your outer layers, and it usually starts off, I think, at like 1/2 ounce thick, and then through the electroplating process to do all of your plated through holes, that will kind of bring the outer thickness up to 1 ounce. But most of your inner layers will tend to be, I think, 1/2 ounce. So if you're doing a lot of power stuff, lots of currents, you kind of might need to pay a little bit of attention to that. So, but for this, 1 ounce, absolutely fine. Vias tented, that's kind of more of a, I think, like a Gerber related thing. But basically tented vias are like where you've got vias that kind of just have the solder mask that goes straight over the top of them. So they're kind of all covered up. Whereas you can also have like vias which aren't tented, where, you know, it would make it certainly a lot easier to kind of get in there and, you know, stick in the oscilloscope probe or something in there if you wanted to probe a signal. But that's kind of like maybe a visual thing, perhaps, if you want. You know, you might choose to have all of your vias kind of covered up and coated in solder mask and keeping a more consistent finish. Plugged, I think, is yeah, okay, what do? They fill them with epoxy. I guess that helps to maybe keep the board flatter or something. And here, things like confirm production file, I guess they might just have a look over everything and make sure that it's actually manufacturable, because I think JLC PCB is one of the companies that will kind of just manufacture anything that you tell them to. Because I've certainly had things in the past where, like, I've moved a trace or moved a component footprint and moved a pad over a trace that it wasn't meant to be connected to. And I don't know if they'll necessarily catch things like that, but they, if you select this option, they might go over things with a bit more of a fine-tooth comb and make sure that there aren't perhaps any glaring errors. Remove the order number. JLC PCB does put their order number on the board. So as an example, I think if you can see it just in the top corner there's a little bit of text right there, which is the order number. Some people don't like that. So you can sort of, select to remove that entirely. Or another way to do it is specify a location yourself. And what you can do is you just put a piece of text on the board. It's like JLC, 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 I think. And you might stick it underneath a chip or a connector or somewhere that's going to be covered up by something else, or maybe you're going to stick a label over the top of it or whatever. But you can kind of choose where you want them to put their little order number. So probe test is like just checking that all the pads and traces are kind of electrically connected, so that maybe there haven't been any manufacturing defects that might have caused a trace to to not be etched properly or something, and maybe it etched all the way through and broke a trace. So that would be caught by the flying probe test. Gold fingers. This kind of caught me out with this board. I thought gold fingers meant that these here, which plug into the ISA slot, would be hard gold plated. I kind of then found out that JLC PCB does not do hard gold fingers, but this is kind of like more, I guess it's just sort of telling them that there are actually like gold plated things, and I think you can choose like yeah, like chamfering, so it can make it a little bit easier to insert the card into the slot. So yeah, that kind of caught me out. I thought I was getting hard gold fingers like really cheap, but if you go to somewhere like PCBWay and have a look at the cost of hard gold fingers, you kind of go, yeah, Enig or Hazel might be good enough. Because it is, maybe it's just because they're the only one who does it, so like they can charge anything they want, but it is ridiculously expensive to get hard gold plating on edge connectors. Castellated holes. So these are kind of like, yeah, if you've got little modules like ESP or something, it's basically like a plated through hole that they kind of cut straight down the middle. So you've got little like concave sort of gold or like tinned pads that you could then solder to pads on a PCB. That's only if the board that you're producing is going to have these castellated holes. It's not like if you've got a board with pads on it where you're going to mount something that has castellated holes, you don't need to worry about specifying this. But if you're producing the board that you need to result in having castellated holes, then you would select this option. Advanced options, I guess you've got more stuff here that you can do. There are little help symbols and stuff here that you can get some more information. PCB assembly, like they can assemble your boards for you. I think they only do it maybe for surface mount stuff, but they probably do have through hole components as well that they can do. You need to order the components through LCSC. I think that's who their like JLC PCB's own kind of like component supplier is. And a stencil, like if you're doing surface mount stuff, then you would order a stencil here. And you've got all these other options. So like the framework is like, if you order it with the frame, it's going to come out massive because it goes into this thing that's really meant to go into a solder paste dispensing machine. And if you go and have a look on YouTube, find some videos of like surface mount assembly lines, you'll see, you know, the solder paste dispensing machine, like how big it is. But like, if you can get a view inside it, you'll see the size of the frame. It's like, it's quite sizable. So shipping wise, you'd probably be better off specifying no, and then you can kind of specify a dimension yourself here. I think customize size. And what I normally do is I make the stencil like sort of maybe like 10 centimeters or so bigger in each dimension. And then that gives you a bit of space, like overlapping the sides of the boards, and you know, it sort of gives you a bit of you know, room to lay some solder paste down on, and then you can sort of squeegee it around. But yeah, like if you leave it at about like the default size, for example, you're going to get something that's about, you know, 40 centimeters by 30 centimeters, which is quite big. So you know, that could impact your shipping price as well. So you can make them a lot smaller just by specifying a custom size. The sides of the board. So if you've only got a single-sided load, which is where all the components are one side, you probably only need to specify maybe the top. The bottom, I guess, if you're doing like a board that's a bit of a mixture of surface mount and through hole parts, like you typically see in like a power supply or something these days. The bottom side might need, you know, to be wave soldered, or you know, maybe you do some bottom loaded components and then, you know, send it through for some sort of you know, through hole components that then get soldered on. But you can sort of put both the top and the bottom on a single stencil if you really want to, or you can have them on separate stencils. And then this polishing process, I think it's just once they've cut out all the little holes in the stencil, like how much effort do they put into making sure that those holes are kind of, you know, smooth and like don't have any burrs and stuff like that. Because, you know, for example, if there's a really rough hole and maybe it's very small, when you squeegee the solder paste on there, maybe when you lift it up, maybe the solder paste comes with the stencil rather than sticking to the board or something. I think etching is pretty good, and then like electrode polishing is kind of the next step up. So if you're doing really fine pitch stuff, surface mount, you're probably better off going with electrode polishing. I think somewhere they said they recommend, yeah, so if you've got really fine pitch stuff, like down the bottom there it says 0.5 millimeter, so like really fine pitch like TQFPs and stuff like that, you probably want electrode polishing because that will have the smoothest holes and probably better success in solder paste application. Yeah, and a couple of other bits and pieces, which you can leave most of this on the defaults. Once you've selected all that, you just kind of hit save to cart and go through the process of paying for it. I think we've only got people from the UK left on here. When you order these PCBs, order the was it DPD option? I think no, DDP, sorry. Because that way JLC PCB will collect the taxes and you won't get stung with an extra fee when the stuff hits the UK. So order your stuff DDP, which is I think direct duty paid. All the taxes will be collected in advance. When the package hits the UK, it will just go straight out for delivery. Back in the day, before companies were required to collect tax, you could sometimes get away with it, but like a lot of the times, for example, DHL would then charge you like an additional £11 fee on top of the taxes that were due. So it just kind of added a bit more cost to the, you know, to the project. But I think actually, no, I might be wrong about that, because I think now by under £130, I think they have to collect tax anyway, so everything is duty paid already. But if you're above 130 pounds, select the DDP option so that they collect the tax. Yeah. So I think you're okay with, yeah, just selecting the standard shipping. I tried this last time I ordered some PCBs. Standard shipping under 130 pounds will be like duty paid anyway. Yeah. And I think that's about it. Questions? If anybody's still listening.
Still here, Tom. Thanks.
Yeah, thanks very much anyway.
That probably needed to be like in 2 parts. Yeah. So hopefully, yeah, anyway, hopefully that kind of gave you a bit of an idea of how to do this. But it's something that requires a lot of practice and just sort of, yeah, development over time to get like really good at it and get things to the point where like you kind of like it. So yeah. Yeah, so I don't really have anything more to say. I think I've said enough. So yeah, basically just any questions you have, just fire them away, and yeah, maybe I'll load up and show you one of my other projects that I've built, which is kind of more complete, shall we say.
There's no sort of simulation tool attached to KiCad.
I think somebody was working on something. I think I read somewhere. I've never looked into it personally, so I don't really know. But I do recall reading something about it, or maybe somebody wanted it, but they haven't done it yet, or yeah.
I mean, it looks as if it includes Spice.
Does it? Oh, okay. Probably right here on the screen in front of me, is it? No. But I think, yeah, maybe you can get some plugins or something. I think it's got a good sort of plugin framework, so a lot of people have made all sorts of plugins. There's a really neat old tool. I think it's either a plugin or maybe it's integrated now in version 7, where you can actually produce like a really nice sort of like interactive bomb. So it'll kind of have like the layout of the board. It'll have a list of all the components. You can kind of click on a certain type of component and it'll highlight it where on the board it is. Maybe I can bring that up. So I've probably generated one for one of my projects.
Just going back to the Spice thing on KiCad, or I posted a link. It says KiCad integrates the open source Spice simulator ngSpice to provide simulation capability in graphical form through integration with the schematic editor. So you go inspect. In schematic, you do inspect and then simulator. Whether that's something you've got, I don't know.
Right. I've never played around with it myself. So but here's like the interactive bomb that I generated for one of my recent projects. So, you know, I can kind of select, you know, components. You know, I think it groups them sort of wherever they're similar by like sort of footprint and value. You know, I can sort of select it. You know, I can see where it is on the board. So if you're looking for like a certain particular resistor or something, you know, I can find all of the 0 ohm resistors. Maybe if I just sort of R1, you know, I can just search for R1 and sort of see where it is on the board. And then I think you can kind of, you know, sort of, well, I guess some of the functions of this is to, well, it looks like, you know, you can say whether or not you've sort of ordered it, you know, leading up to the assembly. And then when you're in the assembly stage, you can sort of like, right, I'll place this part. You know, so then within here, you know, you would see, okay, like I've sourced Look at that maybe. I've sourced like all of these 100 ohm resistors. You know, and you just go through as you're building up your order with Mouse or DGT or RS or whoever. You just sort of tick off, yep, I've got these, I've got these, I've got these. And then when you go through the assembly process, you can kind of tick them off, say, right, place them, place them, place them. But this is quite a neat little tool, I thought. I think it was a plugin for KiCad 6. I think I read somewhere that maybe they were going to integrate this into number 7, but maybe I don't know if it made it into the release. So, yeah. That was sort of my most recent project that I actually managed to finish. If I load that up and go into the schematic, this might be a good example of hierarchical schematics, because I've sort of got here 6 pages, 6 different sort of chunks of schematic for this. Some of them are quite simple, others are a little bit more complicated, but like, you know, you can kind of see like I've got all these sort of wires drawn in going between the schematics themselves, but you know, I can just double click on this and go into a schematic and I've got, you know, a lot more detail. You know, this is a very particular piece of schematic for like the power, and all the different power rails, 3.3 volt and 5 volt. I've got a, you know, a relay driver down here going out to a header. I go into my LoRaWAN transceiver. This is quite simple. You know, I've just got my antenna and some other fancy stuff going on here. These are the hierarchical labels. They look a bit different. They're just like a little tiny thing with a name. But you know, if we see here like LoRa TX is sort of an input signal going into the RX pin on this LoRaWAN module, and back over here, LoRa TX is kind of a this one's probably incorrect. Yeah, but this here is like an input signal, so the signal is kind of set up that way. Sensors, so there's a bunch of, you know, I've got an I2C bus coming in here, going into a bunch of devices. Little IO expander with a header that goes off to an LCD. This little board here, which, you know, you sort of stick an LCD display through.
So Tom, when you lay this out, does it all get laid out on one board?
Yeah. So this is all kind of like broken up just to make it a bit easier for drawing the schematic. Then if I go over to the PCB, it is one PCB. So like all of that schematic and, you know, the way it was all broken up and all that sort of thing is, you know, come together as a single PCB here. Look at something a bit more interesting. Yeah, it's, you know, quite a nice rendering. I'm amazed that I managed to find this 3D model of the LoRaWAN module. That was quite, you know, I'm impressed with that. There aren't 3D sort of parts for everything. So for example, like I haven't found a 3D model for my, like the battery holder that I usually use. There are usually, yeah. So, you know, there are 3D models for like headers and sockets and stuff like that. Yeah. One of my favorite things about KiCad is you can go inside the PCB. Yeah, it's kind of interesting. Unfortunately, it doesn't show all the layers. It only shows the top and bottom layer, but you get to see all the vias and stuff going between. Yeah, that's kind of funky. But then you can sort of, yeah, you can scroll in and you know, zoom around and look at all of your, you know, the placement of things. Like maybe I'm sure it helps with like, you know, sort of working out you know, maybe if things are placed too closely together or something. Yeah, that's quite cool. Go to back side to see all the traces on the back. but on the front, you know, and then I can sort of turn off all the surface mount components. And actually, here's a good example. So this is if I want to tell JLC PCB, can you know, like to save a little bit of money, I can, select just to have them place their order number underneath this IC here, which is the microcontroller, which is always going to be populated because it kind of runs the whole board. But yeah, you can sort of specify, I'd like you to place your order number here, somewhere very specific, so that I can just like cover it up and then I have to see it again. Yeah. Back on, and then that's kind of how it look then to nice and covered up. Yeah, that's sort of the PCB design for this. I do actually have, this is a 4-layer board. The other 2 layers are kind of, we just turned off, but they're basically, there's a ground layer and then a VCC layer. So I think this is probably the ground layer, this green one. Yeah, look at the split in it. And then VCC, I could put a split in there as well. And one of them is ground, one of them is VCC. It's definitely green. Green one's ground because I can see that these 2 vias here don't have any sort of pullback around them for the copper. You can see here this orangey brown layer. These 2 vias got some clearance around them so that they're not going to join on, whereas on the green layer, they're very much sort of joined on. Yeah. So yeah, we can go back and look a little bit more around the schematic. So here I've got some, just inputs for monitoring voltages and currents. These go into these little tiny chips here. And this board, actually, when I assembled it, I did it with a hot plate as opposed to using the hot air gun. And that was like probably the best way, or it's probably the best way to assemble surface mount sort of base things. Because like one of the sort of ideas behind this design for me was to do like a project that was like almost entirely surface mount. There's just a couple of things like these are big terminal blocks here, so they pretty much only come in through hole parts. These positions here are for current sensing resistors, so they're kind of through hole as well. And a couple of other terminal blocks here and some bigger capacitors, but like almost everything else is sort of surface mount, so like all of the chips surface mount, all the resistors and most of the capacitors. Yeah, pretty much everything is surface mount. And some like doing soldering on hot plate was like it just came out so incredibly good. It looked, you could look at it and go, this was professionally assembled, like in a factory somewhere. Like that's how good it came out. Like because like I tried soldering one of these tiny little chips here with a hot air gun, and like I had to I did the initial pass with the hot air gun, and then it didn't really quite look right, so I put some flux around it and then kind of went back and did it again, and then it kind of looked a lot better. But doing it the first time on a hot plate, like these came out absolutely perfectly, like the fillets between the pad and the sort of like contact on the body of the chip itself, like they just look absolutely like pristine and perfect. And I think maybe one of the reasons is that like when you're doing it with a hot air gun, is I think that the solder paste tends to dry out and all the flux kind of evaporates or something. So that kind of, yeah, it just doesn't really happen with the hot plate, because it kind of brings everything up to temperature continuously, and it just goes past the point where the solder melts. It just worked like so much better. So if you're going to do surface mount sort of like projects like this, you know, I could really highly recommend getting a hot plate, and especially I think parts like this. I can't remember if these are like 0.5 or 0.65 millimeter pitch on the pins, like incredibly fine, like, you know, tricky to do with, you know, drag soldering, but like first time, like came out brilliantly, like absolutely perfect. So yeah, highly recommended to get a hot plate if you're going to do surface mount assembly, because I've sort of found that to be much better than using a hot air gun. Probably also because like it gets heat into the entire board, rather than just like one little place. So like rather than like trying to heat this one area, like the heat just keeps wanting to spread out through the whole board. With hot plate, you're kind of heating maybe not the whole board, but like most of the board kind of consistently. So you're bringing the whole thing up to temperature. You know, you're not sort of having to fight against, you know, the board wanting to suck all the heat away. So yeah, and especially things like buttons. When you're trying to do them with a hot air gun, they kind of have a tendency to kind of want to melt. Whereas doing it with the hot plate, everything kind of came up to temperature and just went like straight through from like heating up to soldering. The button actually came out like fully intact. So you know, that's kind of another advantage of doing it with the hot plate.
Have you looked at actually getting JLC PCB to manufacture?
If I was going to build like a lot of these, I'd probably do something like that, because you know it's very fiddly. Like all of these like resistance capacitors and stuff like that, they're all 0805 in size, which are pretty small still, but not too bad to do by hand. If I was going to go smaller, like, you know, there's like ridiculous size things which are like the size of a speck of dust. Like I don't even know how a pick and place machine can do these things. I think they're like 005, 01 or something like that. Like it's I think that's sort of talking like is it mils? I think like 0805 might be like 80 mils by 50 mils or something like that. So an 005 by 01 is like what 5 mils by 10 mils or something. Like it's ridiculously small. But yeah, like 0805, like it's very easy to do by hand. Like you can see the parts very easily, very clearly. They're not difficult to pick up. They're very easy to place. They're very forgiving in terms of like if you don't place them absolutely perfect, you know, once the solder melts, the surface tension will tend to like bring them into alignment anyway. So yeah, but yeah, if I was going to do like a big production run, like if I was making a product that I was going to sell, you know, I needed to make 100 or 200 of them or something at a time. You know, it's a lot of effort to sort of sit there, like, you know, picking and placing parts and, you know, that sort of thing. So yeah, you do it certainly for a big run. For a one-off, like this was just a one-off board that I designed for a project. You know, it was fine to do it by hand, and it was kind of fun as well. So yeah.
I was just thinking, like, if you're saying that to do surface mount, you have to buy a hot plate, and you know you have to buy all this stuff, whether actually just paying someone else to do it would actually work out cheaper.
Well, the hot plate was relatively inexpensive off Amazon, and then I've got it and I can use it for every, you know, project going forward, you know, prototyping and that sort of thing. I don't know how much the assembly fee is. I think JLC PCB have got like some deals every now and then where like maybe they'll, you know, you get your first PCB assembly for like $5 or something plus components. But you know, it's sort of something to, you know, just sort of figure out, I guess, on a, you know, personal level or something. You know, like if you don't want to have, or if you don't have the room, or you know, to have all of these tools, then maybe for you, you know, using an assembly service would be, you know, the way to go. I've got a little bit of room to play with. I'm sort of running out as I acquire more stuff, but I have a little bit of room to play with. So, you know, buying a tool here and there is not a big issue, or it's becoming a bigger issue. But yeah, like having, you know, a hot plate for me is, you know, sort of like, you know, I'd like to have one, and you know, now that I've got one, it's sort of like, you know, any projects I do in the future, I can just, you know, I can just order the stencil, put the solder paste down, and then populate some components, and you know, just build a one-off board. Because like, I mean, it's bad enough having like 5 PCBs and then you only need one of them, and you have like 4 of them left over. But I don't know what the minimum water quantity on an assembly is. So like, how much more would I need to spend to get, you know, say if the minimum is 5 PCBs assembled, and then I've got like a bunch of assembled PCBs sitting around doing absolutely nothing. If it was useful enough to give away to people so they could also play around with it, then yeah, fine. But yeah, I don't know. For me, this kind of works. So yeah.
Oh, thanks, Tom. That's been really interesting. So I had no idea about any of this.
Yeah. Schematic design is a bit of a like an art form as well. Like you can see some pretty terrible looking schematics, and then you can see some absolutely amazing looking schematics. And like, I think one of the best sort of things that happened for me in terms of schematic sort of drawing skill, if you will, was actually looking at the schematics of like the IBM PC and stuff like that, because they very much followed the sort of left to right kind of signal flow, sort of, you know, whatever it is, you know, and it makes a lot of sense, like in a way, because it's sort of, you sort of read it, well, I guess for, you know, people who speak like English and stuff like that, you kind of read from left to right, so you're sort of following the signals in from left to right. So that's kind of what I've tried to do here. So for the largest part, you know, most of the input signals kind of come from the left, and then output signals go to the right. It's not always entirely possible to do that, but like where I could, I've tried to do that.